And I'm going to give you a very quick virtual tour of our house for the Onalaska Farm and Homestead Tour. So this is the house we've been building we started 9 years ago, and we had three things in mind when we were building this place. One, we wanted to be very energy efficient, and two, we wanted to use materials responsibly, have them be very durable, and three, we wanted it to be very low maintenance. So first thing about energy efficiency, we wanted it to be very well insulated and have very low heat loss. So you can see on the north side of the house here, there are not too many windows. This is the east side of the house, so we don't have much heat loss. Windows equal heat loss. The other thing about the house is that it's kind of skinny on the north-south direction, but on the south side, you can see lots of windows, lots of solar gain. On the roof line, it's designed so that in the summertime, the sun doesn't come in, so the house doesn't get overheated on the top floor. And in the wintertime, full sun makes it through the windows, it heats the floor. This house is basically a concrete house, so it weighs about 600,000 pounds. So it absorbs heat and it keeps heat. Now hang on a second and I will show you the material that the house is made out of. This is the compost pile. These are some extra blocks we had from building. But this is called Fast Wall, and it's made out of recycled hardwood from used hardwood pallets, and they're cast into basically a giant cinder block, and the wood chips are ground up and then they're mineralized so that they don't rot, they don't have sugars in them that anything wants to eat. They're insect proof. These have been sitting outside 9 years, and really they haven't changed at all. Now the thing about these blocks is that they have insulation built in. These are insulation layers, and then they're filled with concrete in the voids. And there's rebar that you put in for strength, and you can also run utilities in there. So the one other unique thing about these is that the insulation is on the outside. So this is the outside of the house, would be. This is the inside. So all the quote-unquote thermal mass that absorbs the heat, keeps the building at constant temperature, is on the inside. Many other insulated concrete forms like this are made out of styrofoam, and so the insulation is all around it. And also that's an awful lot of use of styrofoam. You're like living inside a giant styrofoam cup. So we like this material a lot better to build with. Next I'll show you the exterior treatment that we used. On the exterior of the house, I wanted something that was very durable, that I wouldn't have to paint ever, that would last for a very long time, and did some research on it and ended up using lime plaster, and that is just hydrated lime and sand, no Portland cement. The thing about this is that it's a little bit softer, something that uses Portland cement. It doesn't want to crack. This finish here is 9 years old, and there's really not a crack in it. This is what they call Roman plaster. All been used for thousands of years, and mortar is made out of that. And some of these buildings are, 2,000 years old and still standing. So this material actually gets harder and harder over the decades and over the centuries, actually, and it basically turns back into limestone. The sand and the lime, the lime just sort of recrystallizes. So even if it does get a crack, it's sort of like a limestone cave that the cracks self-seal themselves. Another good thing about this material is that it really repels mildew and mold and moss. This is the north side of the house, and it's as good as new, basically. You know, not a trace of anything growing on it, because it's so basic, actually, because of the lime. The finish I put on it, it's not showing up real well here in this picture, but I used moss killer, believe it or not, on the outside. Moss killer is ferrous sulfate. You put it on lime and it has this reaction where it basically turns to rust. So you end up with a sort of textured rusty color. So that's the deal on the finish. Here's just a cross section of the finish here. This is a chunk that I took out of the garage to put in a ventilation window. So you can see this is several layers, and it's about 3/4 of an inch thick. It's quite heavy. It also adds to the thermal mass of the house. So inside the house, we have the inside of those blocks, and I put a clay finish on the inside, which is quite a nice warm finish. It's quite durable. If it gets dinged up, you can actually fix it quite easily. Lots of windows up here, as you can see, and these are triple glazed windows. They're fiberglass, so they have very low heat loss. Floors are also concrete, so we're storing and absorbing more heat there. Now the center of the heating in the house is this masonry stove. This weighs about 5,000 pounds, and you have basically one fire in it every day. In this firebox, and it's a fairly big firebox, if you can get some idea of scale here. So what happens is you have the fire here, the heat travels up through the stove, around this bake oven, and then up to the top of the stove. And there's a secondary combustion chamber up there where the fumes get to about 2,000 degrees, and it just burns everything in the smoke. So then the heated air goes down the side and across the bench here, heats the bench, heats this whole massive brick, this whole 5,000 pound thing, and goes all the way up and out the chimneys. And when this thing is warmed up and burning, there's no smoke coming out. You can see the little waves of heat, but other than that, you wouldn't know that it's burning at all. Another thing about building an efficient house is that you want to have good control over the air movement, the ventilation. This house is very, very tight. I want to show you one other thing here, as we can see in here. We used a spray-in foam on the underside of the roof deck. It goes all the way down, and down connects with the walls, so that there's really no air that can get in to the building here, and then all the windows are sealed well. So it's a very tight house. So one, that's good because it keeps cold air from coming in. Two, that's bad because you need fresh air. So what this thing is called an energy recovery ventilator, and what it does is it takes air from the bathrooms, from the kitchen, from the laundry room, sort of where stale air is and humid air, stinky air, and takes it and pulls it through this machine, and the machine takes cold air from the outside, warms it up, and gives you warm, fresh air in the house. So that's what these 4 pipes do. So fresh air coming into the bedrooms and the living room, the living areas, and the stale, warm air going out of the bathrooms, kitchen, etc. And it is really nice because you don't have a cold, drafty feeling, and yet the air is nice and fresh and clean. Just another thing about air control and ventilation. When you have a fire, it needs air, right? So you've got air going up the chimney, and it pulls a lot of air into the firebox. So where does that air come from? Well, it has to come from the outside. So with older wood-burning appliances, that would just suck air through any cracks you have in the windows, doors, and it would be pulling cold air in. So you have a fire, but you're also pulling a lot of cold air into the room as you're burning it. So this actually has a pipe under the floor here that runs out the side of the house, and that's where the fresh air comes in for the fireplace. So we're not pulling any cold air into the house. All the outside air goes right into the firebox. This is downstairs, and you can see the plastered walls here that don't have clay on them. They don't have a finish. And then this is what the unfinished block looks like. So this is stacked and it's finished on the outside, but I haven't done anything on the inside yet down here. There's a wood stove down here also, and it also gets its air from the outside. The house is built so that this downstairs is basically a photocopy of the upstairs in shape, so that this could be a rental unit down here at some point, or it could be caretaker unit, or Kathy and I could move down here at some point and rent out the upstairs. There's a lot of flexibility here. But now I'm going to show you the most fun room in the house, which is the mechanical room, and this is where it all happens down here. All the floors are heated with hot water, and the hot water is actually heated by that big masonry stove upstairs, and then also by an auxiliary boiler here. And this is just an on-demand boiler. It doesn't use any energy unless the heat's on. It just sits here. And this is the whole hydronic system. There's 6 different zones, and these are the valves, so that we can control different areas of the house. We usually don't use heat down here at all, and it doesn't need it because the house is so stable temperature-wise that even on a cold day, it's, you know, in the wintertime it might get down to 50 down here, but yeah, it's quite stable. Another thing that we've done here is that we don't have a hot water tank. We have endless hot water, it says. This is a demand hot water heater, and it also doesn't use any energy except for, you know, maybe a couple watts for its little brain to work. But it doesn't use any energy other than that until you turn on the tap, and then it turns on. And it uses a ton of energy then, because it's, you know, normal hot water heater will use maybe 1/5 the energy that this does, but it'll take an hour to heat up a tank of water. This heats up water for a shower, for a couple showers, and it can do it instantaneously. So I think it's 120 watts, 120 amps, yeah, 30 times. Yeah. Another thing is that we have a hot water circulator here, and typical ones run all the time, so they're pumping water through the house all the time, and that means that heat loss, you're losing heat through all the pipes all the time, and the hot water has to be heated. This, again, only turns on when you ask for it to turn on, so it saves energy all that time. There's nothing we have to turn off when we leave. Everything is already off. Another thing I want to show you, this is the downstairs bathroom, is these concrete countertops. I made all these custom to fit the space. You can see this one is a corner kind of thing. This is just solid concrete, and this is actually Home Depot bag of concrete, you know, $10 worth of concrete, and then some green stain in it. And so that's a $10 countertop. All you need is $10 of concrete and about 2 days of time and a $300 diamond wet grinder to polish it. But I really like the way they turn out, and actually, you know, if you bought a marble countertop or Corian or something like that, it would probably cost more than that to begin with. So I made 7 different countertops, so I think the $300 investment in the diamond polisher was well worth it. One other thing I want to show you before we wrap this up is that we have solar panels on the roof, and I can't really show you those very well, but I'll show you that we have 2 electric meters actually, and that's because one of them measures how much energy we've generated, and that I believe is the total number of kilowatt hours times 1,000 that we've generated since the system's been in for 2.5 years. And then this is the PUD's meter, and this measures the net amount of electricity. So if we're generating electricity, this meter runs backwards. The numbers on it go down, and we generate about 2/3 of the energy that we use for this house. And also the state has some production incentives, so the system we got in about 2.5 years ago, so the system will be about 2/3 paid for by the production incentives, and also some tax rebates. So it's a fairly low cost system actually in the long run. And we'll walk around to the inside and I'll just show you what's on the inside of this. It's generating electricity, direct current electricity on the roof, and I think it's like 400 volts that comes down. It's quite high voltage, so it's fairly dangerous. The fire departments are concerned about it because even if the electricity is cut off, they've got this power on the roof. But this is the inverter, so this takes the electricity, the direct current electricity from the roof, and changes it into AC that matches the AC that the power company is giving. And if we're using electricity, we use it right here. If we're generating surplus electricity, it just sends it back into the grid and somebody else uses it at the time. And one last thing is that we have a Leaf. And so here's the charging station for the Nissan Leaf electric car. And this takes about 3 hours to charge up. If we charge it, if we just buy the electricity from the PUD, it costs about 80 cents for a fill up, which takes us about 80 miles only. And on a sunny day though, we charge it right from the power that we're generating on the roof, so it works really well. And we're just looking forward to the day when they have electric cars that are affordable and that will go more than 80 miles.